Good day, everyone. Welcome to our new session about earth science. So today we will be discussing the last type of rocks, the metamorphic rocks. So meta means change, morph means form. Okay? So rocks that form when a pre-existing rock or the protolith changes due to temperature and pressure or as a result of squashing or shearing. Okay, so metamorphism is the change that takes place within a body of rock and as a result of it being subjected to conditions that are different from those in which it formed. In most cases, but not at all, this involves the rock being deeply buried beneath other rocks, where it is subjected to higher temperatures and pressures than those under which it formed. Metamorphic rocks typically have different mineral assemblages and different texture from their parent rocks, but they may have the same overall chemical composition. Most metamorphism results from the burial of igneous, sedimentary, or pre-existing metamorphic rocks to the point where they experience different pressures and temperatures than those at which they form. Metamorphism can also take place if cold rock near the surface is intruded and heated by a hot igneous body, although most metamorphism involves temperatures above 150 degrees Celsius, and some metamorphism takes place at temperatures lower than those at which the parent rock formed. Okay, so causes and factors controlling metamorphism. So metamorphic rocks were once sedimentary, igneous, or a different type of metamorphic rock. Because of the heat and pressure of magma coming in contact with rock, the former rock changes into a new one. So first, causes and factors controlling metamorphism is temperature. Okay, so the temperature that the rock is subjected to is a key variable in controlling the type of metamorphism that takes place. As we learn in the context of igneous rocks, mineral stability is a function of temperature, pressure, and the presence of fluids, especially water. So all minerals are stable over a specific range of temperatures. For example, quartz is stable from environmental temperatures, so whatever the weather can throw at it. So all the way up to about 1800 degrees Celsius. So if the pressure is higher, that upper limit will be even higher. So if there is water present, it will be lower. On the other hand, most clay minerals are only stable up to about 150 degree or 200 degrees Celsius. Above that, they transform into micas. Most feldspars are stable up to between 1000 degrees Celsius and 1200 degrees Celsius. Okay, so most other common minerals have upper limits between 150 degrees Celsius and 1000 degrees Celsius. So increased heat allows chemical bonds to break easier. So next we have the pressure. Pressure is important in metamorphic processes for two main reasons. So first, it has implication for mineral stability. Second, it has implication for the texture of metamorphic rocks. Rocks that are subjected to very high confining pressures are typically denser than others because the mineral grains are squeezed together and also because they may contain minerals that have greater density because the atoms are more closely packed. Okay? High pressures cause minerals with open lattices to collapse, forming more dense crystals. When forces are not equal in all directions or differential state stress, minerals may deform and change shape. Okay? Next, we have time. Most metamorphic reactions takes place at very slow rates. For example, the growth of new minerals within a rock during metamorphism has been estimated to be about 1 millimeter per million years, while the rate of metamorphism is slow. The tectonic processes that lead to metamorphism are also very slow. So, in most cases, the chance for metamorphic reactions to be completed is high. For example, one important metamorphic setting is many kilometers deep within the roots of mountain ranges. Okay, so a mountain range takes tens of millions of years to form and tens of millions of years more to be eroded to the extent that we can see the rocks that were metamorphosed deep beneath it. Okay? So next, we have the parent rock. So the parent rock is the rock that exists before excuse me, metamorphism starts. So sedimentary or igneous rocks can be considered the parent rocks for metamorphic rocks. Although an existing metamorphic rock can be further metamorphosed or re-metamorphosed, metamorphic rock doesn't normally qualify as a parent rock. For example, if a mudstone is metamorphosed to slate and then buried deeper where it is metamorphosed to schist, the parent rock of the schist is mudstone, not slate. Okay? So the critical feature of the parent rock is its mineral composition because it is the stability of minerals that counts when metamorphism takes place. In other words, when a rock is subjected to increased temperatures, certain minerals may become unstable and start to recrystallize into new minerals. Lastly, we have fluids. Water is the main fluid present within rocks of the crust. The presence of water is important for two main reasons. First, water facilitates the transfer of ions between minerals and within minerals, and therefore increases the rates at which metamorphic reaction takes place. It does not change the outcome of a metamorphic process. It speeds the process up, so metamorphism might take place over a shorter time period. or metamorphic processes that might not otherwise have had time to be completed are completed. Second, water, especially hot water, can have elevated concentrations of dissolved elements or ions, and therefore it is an important medium or moving certain elements around within the crust. So, not only does water facilitate metamorphic reaction and grain-to-grain basis, it also allows for the transportation of elements from one place to another. So these are solutions that chemically react with minerals. Okay, so we have there are two types of metamorphism. So first is the contact metamorphism, occurs adjacent to igneous intrusions and results from high temperatures associated with the igneous intrusions. Next, we have the regional metamorphism, occurs due to changes in pressure and temperature over a large region of the crust. Okay, so this is the diagram of the regional metamorphism and for contact metamorphism. Okay, so we can identify metamorphic through the following. Okay, so first, metamorphic texture. Grains are interlocked and grow in place. Next, we have metamorphic minerals. Certain minerals only grow under metamorphic temperatures and pressures. And lastly, we have foliation. Alignment of platy minerals or alternating layers of light, of felsic, and dark or mafic minerals. Okay, so we have the formation of metamorphic rocks. So first, recrystallization changes the shape and size of grains, but the same mineral remains. For example, sandstone may recrystallize into quartzite. Okay, so second, we have the metamorphic reaction, the result of chemical processes that decompose minerals and produce new minerals. Third, we have pressure solution. Mineral grains dissolve where their surfaces are in contact. And lastly, we have the plastic deformation. At high temperature, minerals can behave like soft plastic and become squash or stretch. Okay, so there are two main types of metamorphic rocks. Those that are foliated because they have formed in an environment with either directed pressure or shear stress, and those that are non-foliated because they have formed in an environment without directed pressure or relatively near the surface with very little pressure at all. Okay, so some types of metamorphic rocks such as quartzite and marble, which can form whether there is directed pressure or not, do not typically exhibit foliation because their minerals, quartz and calcite, respectively, do not tend to show alignment. Okay, so when a rock is squeezed under directed pressure during metamorphism, it is likely to be deformed. And this can result in a textural changes such that the minerals appear elongated in the direction perpendicular to the main stress. This contributes to the formation of foliation. Okay, so during shearing and compression, minerals become stretched or plastic deformation, all while recrystallization and neocrystallization is taking place. Okay, analogy. Think of stirring chocolate fudge into ice cream. The fudge starts out in a blob, but gets deformed and smeared during stirring. Okay? Okay. So these are the example of foliated. We have the phyllite, the chess, metaconglomerate, and the gneiss. And the non-foliated, we have the quartzite, marble, and amphibolite. Okay. We have the progression of metamorphism. So let's start with a shale and then hit it with heat and pressure. Okay, so the soft clay rich rock known as shale. So when shale is subjected to heat and pressure, becomes a harder rock called slate. Okay, so different grades of metamorphism are demonstrated when a shale is subjected to increasingly greater heat and pressure. First, it becomes slate, then phyllite, then chess, and finally, with even more heat and pressure, you end up with something that is really nice. Okay, so that sums up everything. So I hope that you have learned from the discussion today, and see you in the next video, and God bless everyone.